Welcome to M1. Today we're looking at moments, chapter 8. Now in this video, what we're going to start looking at is when we introduce a rotational force into our problems. Now, as we've been looking at mainly particles, we didn't have to think about these kind of rotational forces. But now, as our objects become, say, rigid bodies, we need to think about where the force is going to act on the body. Obviously, a particle all acts in the same point, but in real life, things don't always act in the same point. So when you apply a force in a particular position on a rigid body, the outcome will be slightly different depending on where that force is applied. And that's where this is all going to come in today. Now, to find the moment of a force, which is that turn-on effect on the rigid body, what we need to do is simply multiply the magnitude of the force by its perpendicular distance from its axis of rotation. So if in this case it's already at 90 degrees, then it's just simply the size of the force multiplied by this distance. Nice and easy. And here we have it. The moment of F about P is the modulus of F times D. Modulus of F is just because we're looking at the size of the value and we want the positive size of that force. Now, going with this, we also want to think about the direction. So if I think of this force F, it's going to end up pulling this round in a clockwise direction. So this one actually is the clockwise moment of F about P. Now, it's not always going to be clockwise. Sometimes this force is going to be acting at an angle. In this case, I've just put theta. Now, we always want the perpendicular distance. So we want the perpendicular distance of the force from P. So that's the distance we want there. Now remember, this is still currently D. And if I want this distance here, I need to think of this as, well, Pythagoras, trigonometry, isn't it? Opposite. This is the hypotenuse, this is the adjacent. So you can see here that sine theta is O over H. So sine theta equals O over D. So that O is D sine theta. So that means that this distance here is D sine theta. So now when I think of the formula for this one, it's going to be my F times D sine theta. Okay, so quite simple, quite straightforward at the moment. Just thinking about the distance here is always perpendicular. Okay, always perpendicular. So here my example is just to calculate the moment about P of the force acting on the lamina. So just a reminder, a lamina is just an object which has area but negligible thickness. So like a piece of paper, its mass is distributed evenly across a flat surface. Okay, although actually it doesn't have to be evenly, I don't think. It would usually kind of say a uniform one if it meant evenly, but it's distributed across a flat surface. Now this one's quite easy and straightforward. So we can see that the moment of the 5 Newton force about P, now this is going to be the magnitude of the force, which is obviously 5, multiplied by the perpendicular distance, which is 3. So 5 multiplied by 3 is 15, and the units are Newton meters. And I also need to put a direction. So looking at it, this is going in a clockwise direction. So I would just put then clockwise. Now a similar example, this time we're at an angle. Okay, so it's very straightforward. We've got the magnitude, which is 4 multiplied by the perpendicular distance, which in this case will be 2.3 times sine 68. And that will be 8.53 Newton meters. And then looking at the direction, this time it's going to spin this way, so it's anti-clockwise. Easy enough. I'll give you just a couple of to have a quick little go at, and then we'll move on. Now, sometimes we might have more than one force acting on that body, and we have to work out what the resultant force is. All the problems that you see in M1 will have coplanar forces. That means they're acting in the same plane. Okay, that's quite important. So essentially you're thinking of them as like kind of two-dimensional. Okay, so it does make your life a little bit easier for these. So let's jump straight in with an example. So in this question, you can see there are several forces acting on this rod. It's going to be a light rod. So being a rod means that all its dimensions except for the one, which in this case is its length, are negligible. And the fact that it's light means that its own mass isn't going to affect my question. Now, for a question like this, I want to think about my forces in terms of their direction. So you have your clockwise forces and your anti-clockwise forces about a point. And you can often pick any point, and we'll talk about that in later questions. This one is going to be about P, which we got here. But in some questions later on, picking where you're taking your moments about will make your question or make solving the problem a little bit easier, picking the right place. But like I said, in this one is just the 1 point. So let's have a look at our forces. So let's start off with our 5 Newton force. So you can see that the moment for this one, and all of our moments are about P. So the moment for this one is going to be 5 newtons times a distance of 5. So 25 Newton meters. Now the direction you can see will take the rod in this circular direction, which is clockwise. Okay, now I'll just do these in order, but I do often do them in terms of which direction. It doesn't really matter. So my 7 Newton force, now this is going to have obviously the 7 newtons times 2 meters for the distance, so 14 Newton meters. And then thinking about the direction, it's going to take my rod in this direction, which is anti-clockwise. Now, I've got my 8 Newton force. Okay, again, I'll write this all the way down. I do often skip these ones because you can see it has a perpendicular distance of 0. Okay, that force has a perpendicular distance of 0. Okay, so therefore it's 0 Newton meters and obviously no direction, because it's not going to affect the turning of P. So think of all these forces that affect the rotation around P. You know, if I pull down here, this whole rod would rotate in this direction. This one, if I push this force up here, it's not going to turn my rod. Okay, so that's a way of thinking about it. You know, is it actually going to, think of it logically, is it actually going to turn the rod if that was the only force acting on it? And then my final force here is 2 newtons. So my moment is going to be 2 newtons times 2 meters, so 4 Newton meters. And the direction is going to take my rod in this direction, which is anti-clockwise. So what that means is I have one force clockwise, so you have 25 Newton meters clockwise. I have two forces that are anti-clockwise, and 14 plus 4 is 18, so we are 18 Newton meters anti-clockwise. So I can quite quickly and easily see that this is going to start rotating in a clockwise direction. So, you know, my resultant so this is going to be 25 minus 18, which is 7 Newton meters clockwise. Okay, and that's essentially all there is to this. Now, obviously you can start by picking one direction as the positive, or one clockwise or anti-clockwise, but I find it easier just to total up my clockwise ones, total up my anti-clockwise. The largest one is clearly the direction it's going. Do the largest, take with the smallest, and the direction is the same as the largest. I just find that kind of thinking a little bit easier. I'll give you a couple to have a go yourself, and then we'll look at the next bit. Now, some questions will tell you that the problem that you're looking at, like that rigid body, is in equilibrium. So that would mean that the resultant forces must be 0. Okay, that's the force in any direction is 0. So not just the moment. You know, if it's in equilibrium, say it's like resting on 2 points, it means that the, say, for example, the upward force and the downward force would be 0, the resultant of that, as would the rotational forces, the moments. Okay, so that's quite important when you come to solving these next type of problems. Now, if I get a question like this, my first step has got to be a diagram. Okay, so I've got to put a diagram out to work out, or to kind of visualize what's happening. So we've got a diagram, it's of mass 20 kilograms, okay, and length 8. So if its mass is 20 kilograms and it's uniform, that mass will act exactly in the middle of my diagram. So I'm looking at essentially 4 meters either side of AB. Okay, so that's my kind of first step. Now it has 2 supports. AC is 1 meter, so you think of a support here that it's resting on. A distance here from A to C is 1 meter, and then we have a second support here at D, and this is 2 meters. So we've got 2 meters, and then this is obviously 4 meters, and this 1 meter. So that's so far a lot of my information. Now I also have a woman of mass 54 kilograms standing on the beam at E. Now I don't know exactly where this person's standing, but you can see that the reaction at D is double the reaction at C. So this person is more likely closer to D than to C. So I'm going to put this person on here. And what I've just done is just taken away that kind of 4 meters just to make my life a little bit easier here, you know, and see, hopefully you guys can see exactly what I'm doing. So this one is 54 kilograms. So this is where my diagram is currently at. Okay, now coming off my 2 kind of points here, my 2 supports, we have our reactional forces. Okay, remember that at D it's double, at C it's a 2R and 1R. So at D it's double. Okay, that's it pretty much now. Okay, now I didn't specifically mention in the question that this is all in equilibrium, but it is, it's all in equilibrium. So let's have a little look at what we can do. So the first thing we can do is resolve our forces vertically. Okay, so thinking of the forces going up, we have R plus 2R, and our forces down is 20G plus 54G. So we get 3R equals 74G. So that means that R is 74 over 3G. I won't multiply by the 9.8 yet, as I don't really want to round off my values. Now, I want to think about where this woman stood. This distance here, we're going to call X. It's what we need to find out, the distance AE. And there's a few things in which we can consider here. Now what I would say is, because we want to find this distance AE, it makes sense to take our moments about A. Okay, but I could take my moments about A, C, D, or B, all equally. And in some questions, especially if I've only got one pivot, it would make sense about taking moments about that, because then I wouldn't have to worry about the reactional force. Okay, but in this one I'm going to take it about A, so it's easier to find this distance here. Okay, and I should always say that. So take your moments about A. So this time, let's look at all the ones that are going, since A is on the end, it's nice and easy. We can see that this reactional force is going to have a anti-clockwise direction, as will this one, anti-clockwise. So let's put these on one end. So we've got 1 times our R plus, and then our distance to our second one is going to be 6 meters. So 6 times 2R. Okay, because this, if you think, is 2 meters from here, total 8, so 6 meters from A, This one's 1 meter from A. And these two send it in a anti-clockwise direction. Going in a clockwise direction is my 20G and my 54G. So 20G times X, sorry, not times X, times the distance of 4 plus 54G. This one is times by X. So what I've done now is I've just created an equation where I've got all my anti-clockwise forces on one side and my clockwise forces on the other side. Now it should be straightforward. We've already worked out what R is, so it's just a matter of substituting everything in, doing a bit of dividing and subtracting to simplify and get my X equals. And we should be left with 4.46 meters to the nearest centimetre, 2 decimal places there. Okay, and it does kind of make sense. We expected it to be over the halfway and closer to D than to C, and it is exactly what we kind of expected just from kind of thinking about the problem practically. Hopefully that makes sense. I'm going to give you just another couple of questions and then we will move on to centres of mass. Now in this question, 15 kilograms is going to act in the centre, so 15G. So that means it's 3 meters from A and 3 meters from B. We also have 2 reactional forces, one at C and one at D, which I'm going to call R1 and R2. Okay, now we can't say that R1 and R2 are the same size, we don't know, so we have to label them separately. So we can say that R1 plus R2 equals 15G, but we can't distinguish between them yet. So I want to take moments about C and moments about D separately, as that will get rid of each of my normal reactions into. It's worth noting that I did it by taking moments about C and then moments about D. But alternatively, I could have also looked at the resultant, say vertically, which is R1 plus R2 equals 15G. And once I'd found R1, which we know, sorry, R2 in this case I found first, didn't I? Which was 98. I could do my 15G minus 98 and find that R1 was 49 newtons that way. Okay, so I didn't have to stick with just finding moments. I could also resolve vertically there to find the second value that way. Okay, so you've got a couple of options. Question 8, first step, draw your diagram. So here's my question. Obviously there is a normal reaction coming off the pivot here, but we don't need to work it out for the question, and it doesn't help us in any way. So I don't need to do anything with that. What I do need to do is look to take my moments. Actually, I lie about the normal reaction. It is important if we take our moments about A or B. If we take our moments about M, then it's not important. So there's kind of 2 ways really of approaching this question. So if I take moments about M, then in my anti-clockwise direction, I've got 42G times 3.25. And then in my clockwise direction, I've got 47G times, and it's 3.25 minus X. Okay, if you want to, you could call that distance, say, distance Y, and then find it out afterwards. So that might be another way in which we can do this a little bit easier. So let's maybe do that if you want. You know, call it distance y, and then it's really straightforward, or call it the 3.25 minus x. It makes no difference. I'm going to put it back to 3.25 minus x and find that value of x in one go. So we get a 3.25 minus x, and this is from 42 times 9.8 times 3.25, which is just over 1,000 odd. Divide that by our 47 times 9.8, and we get then roughly 2.9. So I'm going to put 2.9 here. Obviously I'm using the full answer in my calculator, and rearrange for x. So 3.25 minus my 2.9 odd gives me 0.35 meters. This is to the nearest centimeter here. Obviously if I'd use the value y here, then I'd have an answer for y which would have been this, and I'd take it away from the 3.25. So nice and hopefully easy. Now an alternative way, which is probably a little bit longer, but you can resolve, also find the resultant. Vertically, which would be r equals 42g plus 47g, which is 89g. And then we could take moments about b. Okay, and what I can see there then is going to be my 89g times 3.25 is going to be pushing in one direction, and then we've got 42g times 6.5 plus 47g times x. And if I rearrange all of this, I get the same answer. So you can see you can do it another way, take a moment about b, but really, you know, it makes way more sense to take it about m, so you get rid of that normal reaction. Now sometimes we have a non-uniform rod, and if we have a non-uniform rod, then the centre of mass of that rod is not necessarily in the centre of that rod, the midpoint. Okay, could be at different points within that rod, and that's what the centre of mass is all about. Okay, sometimes you might be given the centre of mass in a different position, sometimes you might need to find that centre of mass. So let's look at a question now where we've got a non-uniform rod. So we've got a non-uniform rod, AB, length 5 meters, mass 15 kilograms, rests horizontally, suspended by 2 vertical strings. So first thing we want to do is draw our diagram. So we've got our rod, 5 meters across. We don't know where that 15 kilogram bit is first because it's non-uniform. The strings are attached at C and D, so let's put A and B, and C is going to be 1 meter from A. So that's tension 1, and that's 1 meter. And AD is going to be 3.5 meters from A, so this distance in between them is 2.5 meters. So we've got 1 meter, 3.5 meters from A, so that final one is 1.5 meters here, if we needed it, to get my total of 5. Now the tension at D is twice at C, so while these are different tensions, what we want to do is just call one of them, say T, and the other one then would be 2T. Okay, and then we've got a 15 kilogram weight, and we know that this distance is X. Okay, so the first thing first, we can resolve vertically. So that gives me t plus 2t going up, and that's going to be equal to 15g going down. So 3t equals 15g, so t is going to be 5g newtons. Now I can essentially then resolve again, or take moments about any point on here. So I could take moments about, say, C or D, or A or B. Those are the ones that obviously all make sense. Doing it C would eliminate one of my tensions, possibly making things a little bit easier. But I'm going to take it about A, as I've set this distance here as x from A. So I want to state that taking moments about A. So let's look. Everything now that is going to go up, because we're going about A, these ones are all going to go in this direction, which is anti-clockwise. And then the only thing going in a clockwise direction is this weight. So we've got 1 times t plus 3.5 times 2t. And then we've got 15g times by x. Now we know t already is 5g, so this is 5g plus, and 2t is 10g, so 10 times 3.5, so this is going to be 35g equals 15g times x. So we've got 40g divided by 15g essentially, because I haven't done any kind of simplifying here yet, essentially, but the g's would cancel, so x is going to equal 8 over 3, or 2.67 meters to 2 decimal places. Okay, so the center of mass is 2.67 meters from A. And there we have it. Now, this type of question, this finding the centre of mass might be one part of the question, then the next bit will then be something a little bit different, or they might give you where the centre of mass is, and then you have to find something else within the question. Just remember, when you see non-uniform, it means it's not necessarily going to be in the centre. Okay? If you see uniform, then it will act in the centre. I'll just give you maybe one question to have a go at with this, and then we'll move on. So with this one now, we have a few options. Obviously we need to put an x in for the distance, and I want to think about where I'm going to take my moments maybe. So I could put x here and take moments about A, put my x here, take moments about M. Okay, put my x kind of from here to B. It doesn't really matter, so there's a few different ways of solving this. Now I'm going to take my moments about M, so I don't have to worry about that normal reaction. So I'm also going to put this as my x distance, just to make my calculation a bit easier. Now, the final thing to consider is when something is on the point of tilting, okay? So if this was on the point of tilting, imagine it was on the point of tilting about C. Okay, it's about to tilt. What that means is that there's absolutely no weight resting at D, because this is just about to move up. This is just about to tilt. It means this side's going to drop slightly, this side's going up. So if it's just about to tilt about C, it means that at D, there'll be no normal reaction because there'll be no weight being rested at D. Okay, it's just at the point where it's about to lift off D. Okay, so what that means is that initially we would have reactions at both of these points, and when it's about to tilt at C, that one would disappear. Okay, or if it was about to tilt at D, this one would disappear. Okay, so if it's about to tilt at a particular pivot point, okay, any other support, okay, including tensions in wires and strings, etc., would be 0 for the reaction. Now, let's have a look how this translates within a question. So, as in all these, we want to start off by doing a quick little diagram, a little sketch. Now, if it's about to tilt at D, that means we do have a reaction at D, but we don't have a reaction at C. So what I want to do is I want to actually going to take my moment about D. That way then I don't have to deal with any reactional forces. Now, don't forget the weight's in the middle, so it's only 0.4 meters from D. 1.5 take away the 1.1. And then I've only got two forces to deal with, my 12G and my 32G. So this makes this question now really straightforward. Okay, so it's just a matter of a bit of rearranging to get my X, and then remembering that that's that distance we went, this total distance. So 1.1, 3 minus 1.1 is 1.9, and 1.9 plus my 0.15 is 2.05 meters. Very easy.